We just finished proving that if you calculate the electric flux through a closed, now this was important, it was a closed spherical surface, then, and the electric flux was how much of the electric field was perpendicular to the surface, added up over the whole surface. What we found was, in this particular case, we had a charge Q, and here was our spherical surface of radius r. And because the electric field was a 1 over r squared field, this came out to exactly Q over that constant epsilon naught. Now, that's true for a single spherical surface of radius r surrounding a point charge. But what we'd like to do is generalize this result. For instance, we would like to say that if we had a variety of charges, so let's take Q1, Q2, say Q3, and we pick any arbitrary closed surface, then what we'd like to show is that the flux of the electric field through this closed surface, it's arbitrary, it's not spherical, is equal to the total charge enclosed. And in this case, the charge enclosed is Q1, Q2, and Q3 divided by epsilon naught. And our goal now is how are we going to go from this nice simple result that depended on the electric field being an inverse square field into a more general case. And so we'll start to do that proof now. What's important to show is that our first step, so the first step, 1, is that if no charge is enclosed, then the electric flux E dot n hat dA through a closed surface is equal to 0. And then we'll generalize and extend that until we get to this result. So that's what we're after right now. We now would like to begin the general proof of Gauss's law. And because this will require many steps, let's just make the statement here of what the general statement of Gauss's law is. If we look at the electric flux through any closed surface, doesn't have to be spherical, let's call it S, then this is equal to the charge enclosed in that surface. So we'll just write this out in words, charged enclosed divided by a constant epsilon naught. And this has the name of Gauss's law. Now, in order to prove this theoretically, we've already shown it's true for a single charge in a spherical surface, and our next step is the following. Suppose we have a charge Q, and I'm just going to do a little drawing here. I'm going to create a closed surface that looks like this. So this just takes a little bit. OK. Now, my closed surface is defined by this solid angle. And let's now look at a few aspects of this. For instance, because this is a closed surface, n was always outward. And so here we have, I'm going to call this n hat 1. This surface here will be 1. And on this surface, because it's point charge, and let's just make our charge positive. That way, our electric field points away. And we have an electric field that goes outward that goes like E1. And on surface 2, our electric field is not as big because of the inverse square. So that's E2. But the unit normal also now points outward, n hat 2. So right away, we see that if we want to calculate the electric flux through these two areas, and let's call this A1, and this one is A2. So the electric flux through this particular closed surface, E dot n hat dA. Now here's the key thing. Because the electric field is anti-parallel to the outward pointing unit normal in this closed surface, our first piece is minus E1 times A1. And remember, E is pointing radially outward, so it's perpendicular. We're making this very small, so we're not worried about any deviations of E being non-uniform. This is a very small solid angle. And on the second one, we have both E and the unit normal are pointing in the same direction, so we have E2, A2. Now, what we know for a solid angle here, a very small solid angle, that the areas, the ratio of the areas here, and if this is a distance R1, and going out here is a distance R2, then the ratio of the areas goes like the distance squared, and the ratio of the electric fields goes like the inverse distance squared. So we have 1 over R2 squared, 1 over R1 squared, which is R1 squared over R2 squared. And now what we see when we calculate the flux, let's write that out. Through the closed surface, we had E1, A1 plus E2, A2. And now let's make our substitutions. And over here, we're going to make the following substitutions. We'll have for E2, E2 is equal to E1 times R1 squared over R2 squared. And A2 is equal to A1 times R2 squared over R1 squared. And now you see that all the radiuses cancel here. And the reason this is working, remember, is precisely because the electric field is a 1 over R squared field. And what we're left with is minus E1, A1 plus E1, A1, and we get 0. And so this was our first step. Through this wedge with a fixed solid angle, the electric flux is 0 when the charge is not enclosed. And again, the reason was that the flux was negative on this face and positive on that face. And now what we'd like to do is start to generalize this for an arbitrary surface, closed surface. Our next step is we'd like to modify this wedge surface. And I'm going to modify it in a very simple way. Let's take this face here, and let's change its orientation. So what I'm going to do is I'm going to draw a line like this, another one down there, and over like that. And so what I've done is instead of having these two nice faces in which the E field and the normal are perpendicular, I'm going to replace that end with a different end here. And I just would like to keep this one line. So now what about the flux through this one? Well, once again, we see that the electric field is pointing radially outward. That hasn't changed. But what's changed, and this was our E2, what's changed is the normal to the surface. So our surface normal is now at an angle n hat 2. So this angle here, theta, is also equal to that angle, theta. And let's look at the area A2. So we'll take our area A2. Now, the area, if I call this piece L, and the other piece, which was the same, W, this is still L times W. And if I call this piece S here, coming down, we see that L is longer than S by S over, because it's adjacent, cosine theta W. And S times W, well, if I went back to my old figure, S times W was just, we'll call this the primed area. This is the old area A2 divided by cosine theta. So what we see is that when we look at this closed surface with one face here and the other face there. Remember, these other four faces, there's no flux, and that's because the electric field is along the surface and the unit normal is perpendicular. So there's no flux on those other four faces. On this face, the electric field is no longer perpendicular to n hat, parallel to n hat. What we have here is that E2 dot n hat 2, and let's write this primed. E is the same, but our unit normal is different. Well, that's the magnitude of E2, but times the angle between the cosine of the angle between them. And so our flux on our new surface, let's write that as E2 prime dot, well, we don't need the prime for E2 because it's the same electric field. It's just the n hat that is no longer the same. And the area A2 is primed. Well, we just saw that the dot product is E2 cosine theta. And the area element is A2 divided by cosine theta. And so we get E2 times A2. And this is what our old result. And here, we don't have to call it dA. We can just call it A2. This was the old flux. So when we look at this surface here, the flux through this end cap is exactly the same as our previous example. And so once again, we see that the flux through this closed wedge of E dot n hat exactly follows the calculation that we had before, is 0. And that's the next step in our trying to get to our general result through any closed surface. Now we would like to try to continue the proof of Gauss's law, where we're showing that the electric flux through a closed surface is equal to the charge enclosed. But what we've been working on first is kind of a zero result. If you have a charge Q, and we take any arbitrary closed surface now. We looked at some special closed surfaces before, so I'm just going to draw an arbitrary closed surface. And this is a closed surface. And now what I'd like to do is look at the result that we had before. If I divide this, if I make small wedges through this surface, so I'm going to make very tiny wedges through this surface. And if outside here, the artwork here, a little tricky to draw. Let's say these lines intersect the surface over here. Now, this may not be perpendicular to the E field, to the actual shape of the surface, but I'm approximating the surface by a piece there. And out here, I'm doing a very similar kind of approximation. And if the angle here is extremely small, I'll use that symbol to indicate this solid angle is very small, then what I can do is we know that the flux through these two faces are 0. And then I make what we call an infinitesimal deformation, where I just kind of try to approximate the small shape of this surface by a very tiny small surface patch. Now, in the limit in which we make the wedge very small, I can divide up this arbitrary closed surface into these two pieces with area A1 and area A2. And now we can go back to the proof that we showed before. Because Q is not enclosed, and if I have to tilt this area to match the local shape of the surface, well, that's OK, because of the way the cosine factor is canceled on both of these pieces. And so for this infinitesimal surface, we have that E dot n hat dA1 plus E2 dot n hat 2 dA2 is 0. And that was what we did. We proved in our last video. And now what we do is we just add up a surface integral adds up all these pieces. And so as we extend our surface over the whole piece, we're dividing up our surface into these wedge-like shapes. And so using this infinitesimal argument, the sum over the whole surface of E dot n hat dA over the closed surface. Now, sometimes I'll write little dA, or I might write a big dA. That doesn't matter. That's just a letter indicating the small area element. When I sum up all of these over the whole surface, the pieces that are in pairs will cancel, and this is 0. And the reason it's 0 is that there's no charge enclosed. And so that generalizes what we did for the wedge and tilting the angle of the wedge to an arbitrary closed surface where the charge Q is lying outside the surface. And now we're in position to try to prove the general result. We're now in position to start our general proof. Let's suppose we have a charge Q. Let's make that positive. And let's look at the following closed arbitrary surface. So here we have an arbitrary closed surface. And what I'd like to do is surround this closed surface inside the charge, not surround it, but let's put a spherical closed surface here. So this is a spherical closed surface. Let's call that S1. The outer one is S. Now, here's the interesting thing. If you think about the geometry of what I've constructed, I've surrounded Q with a closed sphere. I have surrounding the whole thing a surface S. But I now have a surface that consists of two pieces in some way. It has an inner surface and an outer surface. And I want to call this S prime. So my surface, my closed volume, has an inner surface, which is spherical. It has an outer surface, which is the arbitrary closed surface S. And notice that the charge Q is not inside this surface S prime. So we've already proved that as far as S prime goes, that the electric flux dA is 0. Now, what that means is that there's flux coming into the surface, which will be negative, because that's our E field. And there's flux going out of the surface, which is kind of very complicated, because the surface area is not nice like a sphere. But the fact that the total flux through this shape is 0 means that the flux that comes in is equal to the flux that comes out. So we can restate this statement as the flux E dot n hat dA, and I'm just going to write in. Now, the in is the spherical surface. So again, that's the flux that's going into our closed surface S prime is equal to the flux E dot n hat dA out. And the out is our closed surface S. And we've already calculated the flux through a spherical surface. We know that this is Q over epsilon naught, and that's equal to the flux E dot n hat dA. Now our outer surface, closed surface, S, and so we have our next step, which is to show that if I put a point charge in space and I surround it by an arbitrary closed surface, that the flux through that arbitrary closed surface is just the charge enclosed divided by epsilon naught. And we have one last small step to go. Our last step in proving Gauss's law is to show this is true for many charges. We proved it for just one single point charge. So now let's look again at the following situation. Suppose we have charge Q1, charge Q2, and charge Q3, and an arbitrary surface that's closed, surface S. Now, the electric field here is going to be the total electric field that's coming from this entire collection of charges. But we know, and this is the beauty of the superposition principle, that this is the sum of the electric field of the individual charges. Now, what I'd like to do is treat each charge separately, as we did before. So let's pick a spherical surface around charge 1, a spherical surface around charge 3, and a spherical surface around charge 2. And for each of these spherical surfaces, we've already calculated that there's electric flux going out of these surfaces equal to the charge enclosed. These fields, my drawings aren't, my spheres don't look like spheres, but it's OK. So through each one of these spherical surfaces surrounding the charge, we know that the flux is just equal to the charge enclosed. And as we did before, let's just consider this very complicated closed surface that has spherical holes cut into it wherever the charges are. And we know that there's no charge in this complicated surface that has an inner and an outer surface. The outer surface is the one we want. The inner one consists of these 3 spheres, so it has 3 holes. It's unusual topology. And what we know is that the flux that enters into this surface is equal to the flux out. So we have the statement that the flux through the closed surface S, E dot n hat dA, that's what we're calling the out part of the surface. So the flux on the outside, which is the total electric field, and again, the dA, that can be, we've been using as a convention, capital A, it doesn't matter. That's equal to the flux that comes in, and that's equal to the 3 spherical fluxes through, we'll call this, each of these S1, S3, S2, E1 dot n hat dA, just to write them all out. S2, that's the spherical flux, the flux of the electric field through that spherical surface. And finally, the spherical flux through E3. And there we're seeing the superposition in principle in action. And each of these we've calculated separately. That's Q1 epsilon naught plus Q2 epsilon naught plus Q3 divided by epsilon naught. So we'll write that as the charge enclosed. I'll make a parenthesis here, comma, S divided by epsilon naught, because this is the charge that's enclosed in our surface S. And so what we see is that we now have proved Gauss's law for an arbitrary surface S surrounding closed charges. The next step is to look at a lot of applications and examples, which you will see in a sequence of videos.